So after this little piece right here of knowing all the little details, because now I want to take everything that you knew from yesterday, and I thought yesterday was a great day, by the way, in terms of you guys thinking about this material in a different way and fighting through that. So I looked at it as a positive day for sure. But now I want to just take that information from yesterday and now concentrate it into these small little details and take everything I've learned and kind of apply it to how we measure entropy of the universe, okay? So this is a formula. So that's what we're going to do. We're going to go over that and look at all the possible conditions of how the entropy of the universe can increase or decrease with the variables that affect free energy, okay? Now, so you guys did a form last night. You struggled. Hopefully after this, me doing this live and giving you a good example, that will clear things up. And then we're going to move on to a particular energy system called cell respiration, okay, is how the cell actually gets the energy, okay, utilizes it and uses enzymes to get free energy to run the cell, to couple, okay? So the gosh darn specifics now, and you're ready for this, is this equation, okay? And this, of course, is delta G. It's Gibbs free energy. We measure free energy of the universe by this equation. Now, in AP Chem, we'll derive this from scratch, but the bottom line here is when you look at this equation is that we have two parts to this, really. We have the heat, the change of heat. Heat is not free energy, okay? Heat flowing. Heat flows out of something, you get colder. Heat flows to something, you get warmer. That is not the same as free energy, okay? That's something you have to understand, all right? And of course, we have the delta S. So what's interesting about this equation is that we can look at the individual values of what's happening to a system and apply it to the entire universe if we keep temperature constant, okay, and pressure is constant. Those are some things that we'll talk more in detail in AP Chem. But whether I'm AP Chem, AP Bio, AP Physics, this is the laws of the physics. This is the law of nature, and we have to follow it either we're living or not. So obviously, living things have learned to adapt to how the universe works. So no matter what course I'm teaching, this is the same thing, okay? Any case, so this is the equation because it's really impossible for anyone to try to measure something in the entire universe. So this equation is made or derived to be able to look at a system and then apply it to the surroundings, okay? So what we have here is heat flowing in or out of a system. And then, of course, this delta S is something we can measure. This is the delta S of the system. So this is the system's delta S. We can't really measure the delta S of the surroundings. What's the surrounding? Anything outside the system. I've been drawing these boxes before, okay? Hey, the system is where the chemical reaction could be a cell. This is the rest of the universe. It's really, really difficult to try to measure the entire universe outside your single system. So to measure these things, we look at the system's heat. So this is the delta H of the system, the change of heat, not free energy, okay? Heat of the system, and of course the entropy of the system. Now we know something already. The entropy of the system is always about the degrees of freedoms of the particles. Hey, a solid going to a liquid. Hey, solids are three-dimensional crystals that vibrate in their fixed positions. Liquids are free to move out. And of course, a gas is when you have individual liquid molecules flying around, okay, hundreds of miles an hour. So they are, of course, have a greater degree of freedom. Or we look at, hey, a chemical reaction. Like if I take A and 6 B's and I make, these are just fake chemicals, and I make 6 C's and 6 D's, kind of like if I have glucose, okay, which is C6H12O6 plus, hey, 6 oxygen molecules gives me 6 CO2 gas molecules and 6 water molecules. Hey, I've got 7 molecules becoming 12. More degrees of motion, dispersion of energy, okay? So any case, we'll get to those specifics. So what I want you to understand is this equation is a way to measure the universe's change in free energy, which is equivalent to delta S of the universe. It's a way for us to look at an individual system's changing of its individual entropy and its change of heat going in and out, and we can apply that to the rest. Yes?
On the AP test, do we get like a reference table like with all the compounds on it?
Yes. Okay, you'll get some of this. Most of this you just have to understand the concepts. Yes?
Is the delta H like the enthalpy? Are they the same
Yeah, they
thing?
call it enthalpy.
So it's like the heat.
Oh.
Yes,
The heat is
enthalpy, entropy. That sounds similar. So this is the enthalpy. Great job there. And this is entropy. This is the change of heat that goes in and out of a system. Of course, this is the dispersion of energy of the particles of the system. Okay. All right. Now, let's make sure we're on the same page here. Delta G, that's negative. We all know that we're starting with a graph that's high and going low. It's spontaneous. And the delta S of the universe is positive. Okay. Delta G, that's positive. Hey, that's a graph where we're starting what? Low and going high. You have to add a constant supply of energy to make something in your system have a lot more free energy at the end than the beginning. You're concentrating your source. The only way to do that is you're kind of concentrating energy. Delta S of the universe, okay, is decreasing. That's bad. Yes?
Do you know the difference between delta S of the universe and delta S system?
Delta S is the entire universe for a process to actually happen. Any process that's happening, okay, without an input of energy, somehow energy is being dispersed. That's the pathway. So how do you discern? I think today I'll definitely help you with that, okay? I was getting to that last weekend when I talked about in a universe, if free energy comes out, okay, that's going to make these particles go faster. I was talking about that. We're going to get to those details right now. Okay. Now, one more value of delta G. If delta G is 0, what does that mean?
Equilibrium.
Equilibrium, and that's where you get that graph that doesn't make any sense where the two lines would equal each other. Nothing's going to happen. That's the death of a cell, death of a chemical reaction. The forward pathway is going just as fast as the reverse. There's no preferred pathway, okay? And that, of course, is equilibrium. We'll talk more about that Monday. Okay, let's get into this, okay? Let's get into this. So again, we use this equation to use the system values to get the overall delta S of the universe. Okay, so what I call this one is the always rule, okay? So this is the always rule. Let me explain. When I say the always rule, this means that the process is always going to be spontaneous, no matter what, as long as these conditions are met. Let's look at the formula. Delta G is equal to delta H enthalpy, or change of heat, minus the temperature times the delta S. Okay, remember these are system values. Okay, now let's make this a reaction where energy is released. So here's my system. Okay, and we're going to release energy. Okay, so energy is being released there. All right, so we're going to make the delta H, okay, negative. Why negative? Because here is my system. It's losing heat. It's getting cooler, or the surroundings is getting warmer. So that's a negative, okay? That winds up being a very, very favorable thing. Anytime a system releases heat, what's happening to the surrounding molecules? Aren't they going to go what? Disperse and get warmer? That's a positive. So anytime delta H is negative, that's a favorable.
So the
favorable.
entropy would increase.
What's that?
Entropy.
So the entropy of the surroundings is definitely increasing because of that heat. Very good. So that's why that's very favorable. Okay, now there's two factors in measuring the delta G and thus eventually the delta S, what's the heat doing? Going in or out? And then what are the particles doing? So don't forget I have a minus sign. Temperature is going to stay constant, so we're just going to leave that alone. Okay? And so I'm not going to really put it here. I'm going to eliminate it because it's not changing. Okay? And now I'm going to put the delta S here. Now, in the case of del always rule, okay, I'm releasing heat and my particles inside are going to increase their degrees of freedom. An example would be something like, hey, AB molecule breaks apart into A and B. Clearly this is one molecule and I broke apart into two. We would call that anabolic or catabolic.
Anabolic. No, catabolic.
Catabolic. Anabolic is like building muscles, right? Anabolic steroids. So that is increasing the degree. You had one thing vibrating, it breaks apart into two. They're individually doing their own thing. That's a dispersion of energy. So this would be a positive value. Another favorable. So that's a fave. And so this is favorable, and that is favorable. Okay? Those are two conditions that independently increase the entropy of the universe. One, I release heat. Hey, the surrounding molecules vibrate more away. Hey, the particles inside are increasing in their degrees of freedom. So both of those individual factors are what this delta G is about. So this is the always rule. No matter what, when you have those two conditions, this is always going to be spontaneous. The other day, what did I do? I burnt a piece of paper. Okay, wherever that is, it's gone. Okay, maybe it's here. Whoop, nope.
It's burned.
I'm burnt. Okay, oh, it's on the floor. Hold on. Gotta go in the cellar.
Is your back still in pain?
Oh, yeah, that's right.
Do you
So,
with the-
yesterday I burned a piece of paper a couple days ago.
Did you do your yoga?
Burning, no, I haven't yet. Okay, burning is very spontaneous for obvious reasons. Going backwards doesn't occur. You never see the paper reforming, okay? So it's very spontaneous, which means it has a tremendous pathway forward. But why? We're releasing heat, which makes the surrounding molecules dissipate. And, hey, solid cellulose, made of glucose by the way, is becoming free gases. CO2 is flying around in water vapor. So a solid is becoming gases. So let's see if the charges make sense. And that's what the point of last night's form was. So a minus minus a positive. This is where maybe I confused you yesterday. Well, we always like in math do plus to negative. Okay? So we like to change that. So when you have a minus minus a positive, you're always going to get a negative. Now if you don't see that, I'll draw it again. So here's a minus minus a positive. And what we tend to do is remember it's this. We do plus the negative. So eventually, yep.
No, in math, two negatives make a positive.
Yeah, two over. no,
Okay,
multiplication.
please put any number in your calculator. Any negative number minus any positive, it's always going to come out negative.
That's
Okay.
a
Okay?
multiplication thing.
So this is all we're doing. So all I did is something that I learned when I did math. Maybe they did it a differently way. Anytime you have this setup, I don't care what numbers you get, you're going to always
Yeah.
get
Oh,
a
yeah.
negative value. And again, the way that I learned it is we're going to make that a positive, we're going to flip that sign. So a minus minus a positive is really plus a negative. So a negative plus a negative is always negative.
When I was answering the questions, I thought it was like, cause you know how there was a negative, negative, positive?
Yeah.
I thought the G counted, the delta G.
Oh, okay. Again, you're going to redo that this weekend. So essentially what do I have here is a negative plus a negative. And what's that always going to give me? Always. I always get a delta G that's negative, no matter what. So it's always rule. So things that are tremendously spontaneous, combustion, burning, is always going to be spontaneous because we're going to make free molecules, mostly gases, and we're going to give off heat. So that is the always rule. Okay? Now, let's do the never rule. You probably can guess what that is. The never rule. Okay, same formula. Delta G, delta H, minus T delta S. It's a way of taking the system's change of heat and the system's entropy change and applying it to the entire universe. Okay, so in this case, we have a system, but in this case, okay, I'm going to make the delta H positive. This means that energy is going into my system. That's why it's positive. So that means that, I should say heat, not free energy. Heat. This is heat going out, right? So heat is going into my system, okay? And that makes this positive because the system's value is going up, okay?
Is that not favorable?
That is not favorable. That is one of the most non-favorable. Yep, not favorable. Okay, why not? Well, because the surrounding gas molecules are now going slower if heat is lost by the surroundings and gained by the system. So the molecules are moving a little slower, which means they can't disperse out. Energy is not. So in terms of the surroundings, okay, the surroundings entropy is decreasing, but that's a bad thing. Yes?
I thought colder molecules vibrate slower and move slower, and then fast molecules.
Absolutely correct.
Oh, that you said.
So these molecules that are around here are now going to move slower,
Mm-hmm.
which means they can't dissipate as well. That means the entropy of the what? Surroundings decreases. You can think of this term right here is measuring the entropy of the surroundings by the heat flow of the system. Because the same heat that the system grabs is the same heat that the surroundings loses. That's how it works so nicely. Okay, now let's do another unfavorable process. Let's make delta. Let's take this, do the reverse of this reaction. Let's say we take A and B chemicals, and they come together anabolically to make AB. Well, the delta S of my system is bad. I'm losing the degrees of freedom. I'm not dispersing, I'm putting things together kind of like what things in life does, right? Living things put things together mostly. So this is going to be a negative, which is an unfavorable. So this was a fave. This was a fave. Both of these are unfavorable.
That's anabolic now, right?
Yep. But listen, anabolic alone doesn't mean that, what? Just looking at this alone, you have to consider the heat flow. It's a combination of two factors. That's what this formula is about. Okay, so,
So the top one is catabolic?
yes, because you're breaking it down.
Okay.
Okay, now, that alone, though, doesn't drive the process. So we do the math, okay? Remember, there's a what? A minus here. Now, I'm going to do the same thing. I've got a positive minusing a minus. I learned when you deal with that, you do what?
Plus plus.
You do plus plus. Okay? Bottom line is if you put any number as a positive and subtract it by a negative, guess what you're always going to get? You're always going to get a positive value. Yes?
Wait, so when we would answer in the form, would we do the bottom, like?
Yeah, we're trying to solve for, well, in the form, I'm probably asking you for these values.
Okay.
But then when I ask you to solve for delta G, you've got to do this. Okay? So I will say, hey, what's the sign of the delta S if this is occurring? Oh, we're putting together, that would be a negative. What's the sign if heat's going to the system? That's a positive. What's the actual sign of delta G? Now you got to do that to interpret that. Bottom line is delta G is always positive when you have both of these unfavorable. And if delta G is positive, the delta S of the entire universe is decreasing, which means always be positive, always non-spontaneous, never a chance to be spontaneous. Can we still make this happen? Sure. We're going to have to couple it with something that's spontaneous. We're going to have to constantly force this to happen. This still could happen, but we're going to have to use some free energy from other source that releases it to make it happen. Yes?
So this would have a positive entropy and a negative.
This would have a,
Positive entropy.
this has a negative entropy
and a
because,
positive enthalpy.
and a positive enthalpy.
Okay,
It's
thank you.
positive because I'm gaining heat. Okay? This I think is being bad. I'm decreasing my dispersion by that happening. Okay? And that, my friends, is the never rule. Now, I'm going to get rid of this. Now we're going to have two conditions of what I call the sometimes rule. Where you can have what I have here, two unfavorables, right? And two faves. But what if I have one favorable and one unfavorable? Okay, it could work if the favorable can be big enough to overtake the unfavorable. That's the sometimes rule. So we'll start this way. T delta S. Okay, and this is part of the sometimes, and there's two of them. We'll call this sometimes A. I don't know, sounds like a song. All right. Now, in this case, I'm going to start with a favorable condition, okay? And that favorable condition is in my system. I'm going to have heat being released. Okay, that gives me a negative delta H for my enthalpy. Okay, but heat's being released. Okay, that's good. But let's say I'm doing what? Let's say I am heat's being released, but I'm let's say a liquid going to a solid. That's bad, right? Liquids have free motion. All of a sudden, they're locked up into what? Less degrees of motion once they're a crystal. Or I could have done what? I could have written that again. Doesn't really matter. Okay? So liquids going to solids is bad in terms of the degrees of freedoms are less. Okay? Okay, minus a minus. Now, of course, this is a favorable condition. This is an unfavorable condition. So you have two things going here. Now, you do the math. Okay, I'll rewrite it here. This is plus, this is a minus. And this would be plus a plus. So I'm just doing what? Plus plus.
I think
Now-
that confuses me more.
Well, I have no other way to do it to try to get the signs.
I
It
get
does
it.
make sense. If there's two lines, what I would think is that those two lines, you draw a line through the middle, it makes a plus.
Oh, that's what I
All
was
I
doing.
know is I grew up with these rules banged in my head, that a minus is really a plus plus. Okay,
Yeah.
so,
What they taught us is they just taught us 2 minuses is 1 plus.
Yeah.
okay.
Like if you
Like,
you can't like
if 6
double,
minus-
you can't do a double minus. It has
Right,
to just be.
yeah, I mean, anyway, so whatever helps you through that, I'm sorry. For me, it's just, it's common knowledge for me that way, and I don't know if they changed the math doesn't change, it's how they teach it and how you interpret it. Okay, so any case, 2 minuses become plus plus, all right? Any case, look what we have here. Once you interpret that correctly, you have a minus being added to another plus. Well, when is this sometimes going to be negative? Well, it becomes negative delta G, okay, only negative if the favorable one is in bigger value than the unfavorable one. Think about it. We want a negative delta G to make the delta S of the universe positive, which means it's a spontaneous and it works and there's a pathway. So we have to release enough heat to make the surroundings go fast enough to overtake the system's bad entropy change. Yes?
The only thing that confuses me is once you change it, then it looks like the entropy is favorable because it's a plus.
Right, well, I'm just changing it for the math. When I ask for the signs, those are the signs, then I change it for to do the math. I get the point there.
So when a favorite overrides an unfavorite, it's a spontaneous.
Yes, okay?
Okay.
So what does this mean? Well, I either have to add more, release more heat. Now remember, don't forget, there's a temperature factor. Think with me for a second. I can't really, whatever the heat is lost by the reaction is, I don't change that. But notice, I'm going to throw the T in here because it makes a difference now. Okay, so I've got these two things. It could be positive, it could be negative, sometimes. How can I make sure this becomes negative? I can't make the negative be any bigger. But here's what I can do. Couldn't I have the temperature drop? If I make the temperature go down, get smaller, won't it lower this positive value? So wait a minute. When does liquids freeze? Do they freeze at any temperature?
No.
They only freeze at low enough temperatures. So when the T is low enough, guess what? It'll make this unfavorable condition,
Favorable.
okay, less of a problem. It'll minimize it. It'll minimize this positive that we get when we're doing the math. Remember, negatives overall mean spontaneous. So doing the math, I want to limit that positive. So at lower temperatures, guess what? It will freeze. It's kind of cool. Water doesn't freeze at any temperature. Water freezes only when the temperature is low enough to give it its spontaneity. So guess what? Water freezing is sometimes spontaneous and sometimes not, based upon its temperature and limiting the unfavorable condition. Yes?
So when the temperature is like below room temperature, like 32 degrees, then it'll be non-spontaneous. I mean, it'll be spontaneous.
Correct.
But when it's at room temperature, like you did over there, then it's non-spontaneous.
Correct.
Okay.
Absolutely correct. And there it is in its details. And there's nothing more. You're taking a junior level engineering class, I'm teaching the same thing. Okay? Physics, bio, chem, anything. Yes?
What happens if you go from a gas straight to a liquid?
Okay, that's called depositioning. That's what snowing is.
Wasn't that like the last question on the form?
Well, we'll get to it. Well, maybe, but maybe. So let's do the other one now.
Solid to gas.
Okay. Sometimes B.
Yeah. No.
Okay, start with the same formula. Okay. All right, so in this case, I'm going to start with let's draw my system. And this time, I'm going to do an unfavorable heat flow. I'm going to take heat from the surroundings and have it go into the system. That becomes positive. That is my unfave. Now, if I combine that with an unfavorable delta H, it can never be spontaneous. So I have to combine that with a favorable condition, and that would be what?
The positive delta S.
A positive delta S, which means I better be doing something, okay, that is increasing the degrees of freedom. Okay, for instance, let's do a
Solid melting to a liquid.
or well, in this case, liquid to a, so let's go a liquid going to going to a gas. Okay, or I could write this. Doesn't have to be a phase change, right? I'm just giving you examples. Okay, all right. So what do we have here? Let's do the math. I'm going to rewrite that. Delta H is positive. Delta S. Delta H is positive. Delta S is positive. This is what? Favorable. That's the signs that you have to put in the form. Now I'm going to rearrange this to get the math to get what delta G is. So I have a positive minus a positive, okay? And so again, I'm going to change it to I'm going to do a plus a negative here. I know people don't like it, but I do plus and I make this negative. It's the same thing mathematically. Sorry if I can't give you a different way to think about it. It's just something that's ingrained in my head.
Did they hit you with rulers?
No, well, in one of my schools they did.
They did?
Yeah, I went to a Catholic school. Yeah, they put your knuckles out if you misbehaved.
Oh, you got the nuns.
And they hit you with the ruler, okay? You know.
I went to Catholic
And that was
school,
religious
too.
school. That was,
They
you
hit me
know.
with the ruler.
Okay.
No, they
Any case, so you can see the math. This is my what? Favorable condition here. Now, the only way that this can be a negative delta G, if what? This value can overtake this positive. That's why sometimes it can be both. Don't forget, we have a temperature that's involved here. Okay, do all liquids boil?
No.
No, they boil only when the temperature is what?
100.
High enough to do what? Make this negative big enough to make the overall thing. So what does water boil at? Any temperature? Well, I mean, it's keeping pressure constant. Water boils at 100 degrees Celsius. So at room temperature, water's not boiling. But I can make it spontaneous if I increase the temperature high enough that makes this favorable condition better than this unfavorable. Which is really what? I'm making the entropy of the what? System big enough to overtake the loss of entropy of the surroundings. This first expression of delta H has now been able to look at the entropy of the surroundings. Okay? And there's nothing more to it. There's no other conditions here. Okay, now, one more thing we need to add. These are always and nevers. What's driving this if it's spontaneous? What's driving it? What's making this happen if it's spontaneous? What condition? Yes, Charlie.
Low temperature
Low temperature or
or a high
right.
like
So
use.
even though we're limiting this, the reason why this could work is because of the favorable condition of this. So we would call this, very important, entropy driven. Enthalpy driven. Why is it enthalpy driven? If this can become spontaneous with the right temperature, it means that this negative is bigger than that positive, or there's enough heat release to make the surrounding molecules disperse enough to overcome the loss of entropy in the system. And if you're connecting what I just said, you're at a college level understanding of this, beyond AP, okay? They make you understand this, but not with these details. I am, because I know you can handle it. You're going to see it again, and I want you to see it. Yes?
I know this is like vague, but why are you like changing it after? Like you do, like for the first one, negative, negative, positive, then it's negative.
Okay, that was 25 minutes ago. I'm doing the math to figure out the charge. I put in the signs of energy, in this case releasing energy, and this is the system increasing, okay?
Would it still work if we did it like the regular math instead of your like?
Yes, it's going to be the same thing. It's going to be the same thing, okay? However you do it in what you were taught, I was taught a little different language, verbiage. It's the same math though, yes.
Okay,
Is
good.
then the last one gonna be entropy driven?
Right, excellent. This is the favorable condition, so this is entropy driven. We have to know this for AP Chem. Do you think it's any different for AP Chem?
No.
Not a bit, not a bit. And I'll tell you right now, most biology students do not understand really what entropy is. That's disorder. They just go away. They look at it. Okay. Oh, absolutely. I want you to struggle. Then I want to fix
Yeah,
it.
no
Look.
clue what the plus minus.
Okay.
Okay, I still have a
just
question about
guessed
Yeah.
the transform though. On the one when we watched the balloons and then we had to choose what it was, there wasn't one that went negative and then a positive.
Give me the scenario again, because I do forget exactly.
It was like the helium and the oxygen in the balloon, and then you were lighting it, and it was exploding.
Right.
And then it was asking what was the first, what was the heat, so the
Okay, because there was an explosion, heat's definitely being released.
So
So that's a negative. Okay, now,
And then the entropy would increase, right?
okay, yeah, so the entropy in the reaction, we're not done. I want to make one more point, so don't pack up and go home yet. I have a demonstration I want to do. I should put this together. So in the form, we had this reaction. We had hydrogen and oxygen making water. Okay, now the reaction looks like this. It's two H2s, so there's two particles of H2 to one particle of O2 to make two H2Os. Now they're all gases. So I take three gases and I'm making two gases. So when you think about this process, hey, three gases becoming two, that's an favorable, okay, delta S of the system. But the reason why it was spontaneous, forget the temperature, there was so much heat released in that explosion
Why it wasn't
that was really a sometimes rule.
Yeah, that's
Okay,
that's
the
what confused me.
particles' degrees of freedom were dropping a little bit, but we had so much more heat that could overtake that.
So it would still make it negative.
Exactly. The heat released was definitely negative, but there was so much heat in that explosion. That means you made the surrounding molecules disperse so much energy that the overall universe's entropy definitely still increased, even though a little bit, okay?
But then why would it say that the entropy was negative?
Because the entropy is bad because this is always the entropy of the system, the particle. Remember, this equation is about the system's values that we use to interpret the entire universe. This is the heat that is lost by the system. This is the entropy that is gained by the particle arrangement. So this is always looking at degrees of freedom of particles. So in the case of that reaction, you have that. Okay, I want to do this demo. Okay, I want to do it together. And it's non-intuitive, but hopefully I could do this. Okay, so I'm going to give you a super, we'll see what happens.
If the temperature goes down, then it becomes spontaneous. Like,
Whoa. You started to make rules here. Temperature goes down, it becomes spontaneous.
for like the sometimes one,
Which one?
the top one. Like if it goes
If
down,
I lower the temperature, T times delta S, in this case, I'm going to limit
You just do the normal.
this unfavorable condition. Positive is bad because we want to go negative. So making the positive smaller once you do the math gives this a chance to be negative overall.
Is there a video with the packet?
No. Just look at the key. You read through the packet. It's really self-explanatory. I can't speak. Okay, it's not that bad.
Okay.
is the packet
If you honestly,
Yeah.
if you look at the key and use the key to do it, that's just reading what I want you to know. Okay.
Okay.
So here we go. Okay, I have this demo here. Okay, now, I'm not going to do it this way.
Reusable.
Okay, hold on. I'm going to do it right here. Stay with me. You guys are going to watch while people at home don't leave yet. Okay, and we're going to go here. And who cares? Yeah, just move stuff out of the way. And if my laptop dies, it's because Connor took my laptop charger.
That's Charles.
I don't even
iPad.
have my laptop out.
Okay.
Oh, that one. I was talking
It's-
about
you
his
can
lap-
take
I
it
thought you
now.
said it-
Okay, that's okay. Now, just make sure, okay, cool. Now, I'm gonna make sure that we can go right from the computer to you guys can see the same thing.
Is there a point in it?
Okay, so,
Yes. Yes, there is.
stay with me. Is my HDMI I'm
Wait.
standing weird
No,
because my
that's
background's,
okay.
okay.
No, it's in.
Now, this is gonna go, please go. Ah, good, okay, now,
Wait, what about the Zoom?
they can see. Okay, here we go. Now, Christmas in July.
Is it a necklace?
Oh my god.
Okay, now what I have here, clearly a liquid, correct? Okay, now, what I'm going to do is I'm going to ask Patricia to gently take her hand and grab this, actually I'll do it from here, okay? Now, let's think about what's happening here. I have a liquid. And what I'm going to do is, with this little disc, make some noise. Okay, now watch what happens. That's
What?
crystallizing.
What?
It's crystallizing. It's going from a liquid to a what?
Solid.
Okay, happening right in front of your eyes. Is that spontaneous?
Yes.
Absolutely, you're seeing it happen. Wait a minute. I've got a liquid going to a solid. Wait a minute. A liquid going to a solid?
But sometimes it won't pass.
Whoa, the only way that a liquid
With the temperature decrease.
The only way that a liquid can go to a solid, isn't that unfavorable? I'm going against the grain for the delta S. Hold on. The only way, you just said it, dude, you got it right. So it's unfavorable delta S, correct?
Yes.
Yes.
The only way that that can work is if what? Heat is being what?
Release.
So is that
Can you
hot?
touch it for me? What's it feel like? Grab it.
Cold. Oh my god, hot.
Of course it's hot.
She said cold.
Of course it's hot. If something
That's
is gonna
burning.
solidify,
Wait, let me feel.
if something is gonna solidify, here you go. If something is gonna solidify,
So hot.
doesn't it have to give off heat?
Whoa.
It wouldn't solidify otherwise.
I thought I didn't understand anything.
You just said it before I said it. My friends in chemistry,
I will.
Wait, why?
cement that's solidifying must give off what?
Heat.
Anything that becomes a solid must give off heat.
So Gibbs,
Anybody put a plaster of Paris, break your arm, break your wrist, and they put a cast on? It was setting. What was the temperature of the cast?
Hot.
Hot, because it was becoming a solid. The only way something can become a solid and go against the grain of the universe is that you must release enough heat to make it happen.
Is this like the hand warmer?
See, guys, it is a hand warmer.
It's a hot hand
Oh, those are
warmer.
hand warmers?
Yes.
I thought they
How
were
long
always
does it
like
last though?
yeah. It's reusable.
Can we take it home?
Yeah. But for me to reuse this, hold on. This is a spontaneous process at doing this. For me to reuse this, I have to heat it, put energy back into it, and then cool it slowly. So it's spontaneous this way. I have to add energy to go the other way. Please don't take them home.
It's never
Okay?
It's never
Have a great weekend.